Hi friends, and welcome back to the Control Engineering Geek. Today we are going to draw root locus for a variation in a system parameter. Let's assume that we have this system here. We have this parameter k that we need to know if it varies from 0 to infinity, how it will affect the pole 0 map of this system here. As you can see here, we need to know the open loop gain of the system or open loop transfer function of the system. We can achieve that by using block diagram reduction, where we're going to treat this inner loop as a feedback system and use a feedback equation for that. We're going to approach to this formula here. This formula or this function here is in the standard format, so we can find the open loop transfer function. So this open loop transfer function, since it's not been it's not drawing for variation in the controller, it is being drawn, it will be drawn for the variation in the k. So we need to write this form or the characteristic equation that coming from out from this transfer function in the standard format here, where we have 1 plus the variable k that we want to know the root locus for it, multiplied by the open loop gain of the function. So to do that, we have the original characteristic equation, which is the denominator here. Okay, so what you're going to do here is take out the values that have k's in it, or the variable that we want to draw the root locus for its variations, put it all in one term and try to divide the whole equation by the other terms that don't have the value k or the variable k. So we have this format here: s to the power 3 plus 5s squared 4s plus 20. So divide all these equations both sides by this part here. So as you can see this part doesn't have the values k in it. So what we're gonna get is this format is particularly originally in this form here. So from this new characteristic equation, we can conclude that the new open loop gain is given in this format. So what we're going to do here is now try to draw the root locus using this open loop gain instead of this open loop gain here. This open loop gain, as you can see, doesn't have any parameter in it, whereas this has the parameter as a complete term. So let's draw the root locus. I used the MATLAB directly here, whereas you can follow the steps, the 6 steps of drawing root locus that you can find in other videos on my channel. The system has 3 poles, 1 real pole and 2 complex poles, and 1 pole, 1 0 at the origin. Okay. Let's make the system a little bit complicated. We're gonna need to know what are the values of the variable k. Keep in mind this k is the variable or a parameter that is a part of the system, and it's not the variable that coming from the controller design. This is a part of the system. So you can think of this k as like for a spring mass damper system. This k could be the constant of the spring or the constant of the damper, or even be the mass of the value of the mass of the in that system. So you want to know how does this parameter affect the whole system when it changes from a certain value to certain value. Okay, so we need to know in this particular system what is the value of this parameter that gives a damping ratio of 0.4 for the closed loop system. Okay, so what we know that if we treat the system as a second order system, we may find that the 0.4, the damping ratio 0.4, the corresponding poles for this 0.4 as a damping ratio must lie on a straight lines that pass through the origin and has an angle of 90 minus sine inverse 0.4, or it's plus minus 66.42. This value or this angle is coming from this figure here, where this is the angle. If we take the sine inverse of this angle here, or the sine inverse of the zeta damping ratio, you're gonna find this angle. What we need to know is this angle, or you can use this angle as well to draw a line. So using this angle, we can draw these two lines. One is for plus 66 and one is for minus 66. What we need to know, what are the values of the poles at this point and this point, or this point doesn't matter, because you're going to take the absolute value for the roots anyhow. So at this point, the approximate value of the pole or the root here is minus 1.04 plus 24j, whereas for this point here is minus 2.2 plus 5j. This is an approximate value as just I estimated from the figure. So what we're going to do here is we are going to take these two values and introduce this in our characteristic equation, whether it's the original characteristic equation or the characteristic equation we draw this root locus for it, doesn't matter, and find out what is the value, or what are the values of k that gives 0.4 as a damping ratio. So let's start with the point P. So we have this characteristic equation that we modified from the original characteristic equation. We can have the value of k in this format. What we're going to use here is, instead of using the Laplace value here, Laplace variable, we're going to introduce our computed or estimated pole when the line crosses the locus or the branches. Okay, now try to compute this absolute value here. What you're going to need, or what we're going to have eventually, is the value of k is plus 0.44. Do the same for point Q. We're going to have a value of 1.4. To check our answer, okay, go back to the characteristic equation and introduce k 0.44 and k 1.4 and try to solve for the poles, corresponding poles. So these poles, when the value is 0.44, it's very close to the poles that we get from this one, is from the pole, from the picture or the plot. And this is when k equals to 1.4. This is wrong. It has to be 1.4. The values, this one that we computed from the plot, is very close to this value here. So we know that at k equal to 0.44 and k equal to 1.4, we may have a damping ratio of 0.4. This is how we draw root locus for variation in a parameters instead of variation of the controller itself, and we can estimate the value of this parameter or even the controller gain for a particular specification we need from the system. I hope this was useful for you.